Okay, so I think I can start whenever you're ready. Okay, I'll begin. So first of all, let me, of course, start by thanking very much the organizers for inviting me and for giving me the opportunity to talk in this very nice conference. I'm extremely sorry that I couldn't attend it in person, and it's really a shame. And yeah, I'm sorry also because online talks are really not that cool anymore, right? So I'm sorry about that. But okay, nevertheless, let me start. So today I would like to talk about some recent work that my collaborators and I did on random permutations. So the basic question that I would like to consider is the usual one. I want to study relaxation in isolated quantum many-body systems. And the problem of relaxation in isolated systems is a very interesting one, a fascinating one theoretically, because we essentially need to explain how to pass from a description of quantum many-body dynamics, essentially using the Schrödinger equation. And so that is done in terms of pure quantum states that are evolving unitarily and essentially are describing the evolution of an isolated system. How do we pass from that to some equilibrium description? Once again, some quantum, if you like, statistical mechanics that is described in terms of mixed states. We are now at equilibrium, and typically this situation describes a system in contact with the bath. So the question is, how do we go from one to the other description? And the simplest way to think about these kind of problems is to think about it in terms of a quantum quench. So the idea is that we prepare our quantum many-body system in some initial state and then evolve it with a Hamiltonian that has not that state as an eigenstate. As we know, the requirement to see something non-trivial is a little bit more subtle. We need to have that our initial state is in fact a large superposition of eigenstates of the Hamiltonian in order to generate some non-trivial dynamics. So this is a very natural problem that was studied essentially since the very inception of quantum mechanics. In fact, there is this work from 1929 by John von Neumann that is proving a quantum version of the ergodic theorem. But a systematic study of this problem really started only in the late noughties. And from a theoretical standpoint, the main questions that one considers in these kind of studies can be grouped into three main classes. So the first one is really just about relaxation, what I hinted at the beginning of the talk. So how can the system relax despite is described by the Schrödinger equation, despite in the end being governed by purely unitary evolution? The second question is, well, assuming that there is some sort of relaxation going on, I can introduce some sort of relaxation. Can we develop a statistical mechanical description of the equilibrium state? So is there a way to describe the equilibrium state without solving the full dynamics? And the third class of questions is, what about the finite time dynamics? Is there a way to actually instead describe or find general features in the dynamics of many-body systems? So these questions have been studied a lot in the last 20 years, and they are not entirely solved by no means, but we, I think, acquired a relatively good understanding of what is going on. So let me very briefly summarize it. So concerning the first question, how can the system relax despite purely unitary evolution? Well, this is just very simply explained in terms of locality. So if I consider a Hamiltonian that has local in space interactions, then what can happen is that although the state of the full system does not relax, if I only focus on a finite subsystem in the limit of infinitely large system, then what can happen is that the rest of the system acts as a bath for my local subsystem, and therefore the state of the local subsystem can reach equilibrium. So mathematically, one can write this condition in this way. So if we consider the time evolving state, we trace out the rest of the system B, we take the thermodynamic limit and then the infinite time limit, then this thing gives us a finite result, a limit that typically exists. The second question is, can we develop some statistical mechanical description? And the answer is yes, we can. Essentially, the idea is indeed very simple. One can describe this equilibrium state for the subsystem in a kind of Gibbs form. So if we find all the conserved charges of the Hamiltonian and then build a form that is Gibbs-like that, then we find a state that is indeed stationary. Now, of course, the interesting question is, what are the charges that one should include in this Gibbs state? And so, okay, this is a problem that has been studied a lot, also by people in the audience, and it's in the end relatively subtle. But to simplify it in a simple way, to state it in a simple way, the charges that matter in the end are those with a local density. Okay, so those that really affect the state of my local subsystem are those that have a local density. And the third point is, what about finite time dynamics? Well, that's by far the hardest of these of the three questions. So can we describe the finite time dynamics of a quantum many-body system? That's very hard. But what we found is that there are a number of quantities that display some sort of universal time evolution, that universal in the sense that looks the same in many different systems. Well, probably the most famous example is the behavior of the entanglement entropy. So if I look at the von Neumann entropy of the reduced density matrix to the subsystem A, and I plot its time evolution, under very, very, very general conditions, I will see a behavior that looks like this. So the entropy will show initially an approximately linear growth, and then a saturation to some value that is indeed just given by the thermodynamic entropy of this equilibrium state. So okay, that's very nice and very well established. The question that I would like to consider in this talk is the following. So what about these features is in fact quantum? So what of the properties that I just described is relying ultimately on quantum mechanics, and what instead can also be seen in a classical system? So this is the question that we studied in this recent paper in collaboration with Katja Klobas from Birmingham, Daniel Maltz from Copenhagen, and Pavel Kost, that in fact recently moved from Munich to Ljubljana. And to study this question, we considered a very simple setting. And we considered the setting of local quantum circuits. So you probably are all familiar with the setting, but let me very briefly introduce it. So we consider a chain of qubits with the internal states generically that are prepared in some simple initial state, which we can think about as a product state. And we evolve this chain by applying unitary operations that only connect nearest neighbors. And we do that in such a way that after two applications of these unitary operations, we connect the full system. So in fact, it's much easier to understand the effect of our time evolution by looking at this picture. So we have here at the bottom our chain of qubits. We apply these blocks, these squares that represent our unitary operation. So this is one layer of our evolution that, as you see, does not connect the full system together. But if I do two layers, then you see that all the system is nicely connected. Okay, so what are the main properties of an evolution like that? Well, first of all, it has strict causality. That's very important. This means the following. If I make a perturbation somewhere, let's say here on the initial state, the effect of the perturbation will be visible only within a causal light cone that is shaded here in the picture. This means that outside the causal light cone, the effect of the perturbation is exactly zero. I cannot see any effect. So in this sense, it's some sort of extreme version, if you want to think about it in this way, of the Lieb-Robinson bound. So in this case, there is no exponential leakage. It's exactly zero. So of course, then the second point is that here I'm studying the one-dimensional version of it. But of course, I can define this problem in any dimension. For example, I can immediately extend it from 1D to 2D by essentially taking my squares and making cubes now as my unitary operations. Another important feature is that essentially because of this strict causality property, a setting like that, a system like that can use to approximate arbitrarily well local Hamiltonians. And systems with local Hamiltonian and final Hilbert space. I mean systems for which the Lieb-Robinson bound holds, essentially. And finally, a discrete time evolution of this kind is a very good model for the architecture of the real quantum simulators that are realized now. I'm quoting one of the first papers on this. Okay, so this is the general setting that I want to consider. But now let me specialize this setting to describe what I want to claim is a classical evolution. So what do I mean by classical evolution in this setting? So what I want to consider is I want to study a specific special family of unitary operations that I want to call circuits of permutations. And these are defined as follows. So first of all, I introduce a special basis, which I will call from now on the computational basis. And in this special basis, my unitary operations are acting as permutations. So meaning that if I consider a state in my special basis, let's say I denote it as SR, and I act on it with my unitary, with my special unitary, then what this will give me is another state of the computational basis. And the way I associate one state to the other is arbitrary. I can choose how I do that. And I will do that according to some function. So for example, right, importantly, this does not mean, when I say permutation, I don't just mean the swap of, for example, two states. It's much more complicated than that. For example, one could have something that looks like the mapping that I depict here for these two. So for qubits, the computational basis for two neighboring sites can be written as 0, 0, 0, 1, 1, 0, and 1, 1. And the operation that I want to do is something like that, right? I map 0, 0, and 1, 1, 1, 1 in 0, 1, whatever. I can do something complicated out of that. So why do I say that these circuits implement classical dynamics? Well, because if I act on the computational basis, then these circuits here are just a very simple classical cellular automaton, right? At all times, if I start from a state of the computational basis, I will be in a single given state of the computational basis. And maybe the dynamics will be complicated, but it's just some classical dynamics. However, if I act on a state that is not just a single state of the computational basis, these circuits here can be complicated. For example, we will see explicitly in the following that if I consider an initial product state, which is, however, not a state of the computational basis, so it's something like product over all sides of some aj times j, okay, and then I act with my unitary operation on it, then this will not remain a product and will develop some entanglement. So, but the setting I described is very general in a sense, and also not very easy to solve in general. It's very complicated. So how can we actually approach this problem in a quantitative way? So the way we decided to go about that is to take inspiration from the very successful idea of random unitary circuits. So the idea there is that one can consider a setting like this, where at each position and time, so each one of these squares in the figure is an independent random unitary matrix, and then compute relevant quantities by essentially averaging over these unitary matrices. And this was very fruitful and provided interesting descriptions for many interesting things. For example, entanglement dynamics or operator dynamics in quantum circuits. So we want to do something very similar to that, and so we introduce random permutation circuits. So exactly like in random unitary circuits, we want to take these squares in this diagram to be random matrices at each position and time, but we don't take them to be a generic random unitary matrix. We take them to be generic random permutations in the sense that I defined in the previous slide. Okay, any questions about this? Is the setting clear?
No, I think it's fine. I don't see any question. Oh, please, sorry.
Yes,
Bob. No. Okay. Okay, no, that's
all good.
fine.
That's fine. Okay, I continue. Very good. So the idea is that I want to study basically a system where at each position and time I have a random permutation. Of course, if I want to do that, then the quantities that I have to study are going to be some sort of average of a replicated quantity. So instead of having the state of the system at time t, I will need to study a replicated state of the system and its complex conjugate, and then average it over all the possible random permutations. So I want to consider the fluctuations of that, right? And in my pictures, I will typically represent the complex conjugate of my unitary gate using a blue color. So here, for example, I have this stack of red and blue colors, and each red diagram represents one copy of this time-evolved state, and the blue one is the complex conjugate. So how do we compute these kind of averages? So let me give you a very quick idea of how to do it, starting from the case of random unitary circuits, just to set the stage. Okay, so let's consider a single unitary matrix, okay? And for simplicity, let's act on a single qubit so that we don't have these two legs that confuse the picture. So now if I have this one stack like those that we saw in the previous slide, and I act on this special state, it's very easy to see that this special state is indeed going to be invariant. And the reason why the state is going to be invariant is that this special state you see is making some sort of pairs between the state in the replicas. And for example, in this case, we are pairing the first replica with the first replica that is evolving according to U star. And so if I act with this matrix on this state, what I'm doing is I'm essentially multiplying U by the Hermitian conjugate of U on each one of these loops. And therefore, this state here is going to be invariant. In fact, this is not the only way I can do that, of course. I can pair the different replicas in many different ways. For example, that's another way to pair the replicas. And once more, I will always, whenever I act with this matrix on this state, I'm always multiplying the matrix U by its Hermitian conjugate, and in the end, I will get something that is invariant. So this means that essentially, it's very easy to construct some invariant states for this kind of matrix. What I need to do is I basically need to pair all the replicas evolving according to U, so to what we can say forward evolution, to the replicas evolving according to U star, which we will call backward evolution. And we can pair them according to essentially any permutation that we like. So whenever we construct a state that looks like this, where here I have S1, and then I will have something, and then S2, something, S3, etc. And this something I associate according to a given permutation, then I will get something that is invariant. Okay. So in the same way, I can construct invariant states for random permutation circuits. the main observation in this case is that a permutation matrix, in the way I defined it, preserves the sum of all computational basis states on a given site. So the so-called flat sum is preserved. So this means that if I consider the sum and I act on U on it, and I act with U on it, I will get again the sum back. So this means that if I now consider a stack of these matrices, and I consider a state that is pairing together any groups of states in the replicas, which are represented with this kind of block of lines joined together. These are all essentially all these replicas here are on the same state, and I sum over this state. Whenever I do something like that, the resulting state is going to be invariant. Okay, so this turns out to be in one-to-one correspondence, not with permutations, but with partitions. So I will take my set of indices, one-to-n, that labels my replicas, and I can essentially do a partition of this set, which I can write as pi in this complicated way. But the important point is that whenever I take a partition of these guys and I set essentially all the indices pertaining to the same subpartition to be on the same state, and then I sum over, I will get a state that is indeed invariant. Okay, so I can construct the analog of this invariant state for random unitary circuits for random permutation circuits. And in this case, the state will be labeled by partitions. So let me very quickly check how many states do I get if I do this. So if I consider these states that are invariant under random unitaries, then I have n factorial of them because they are parameterized by permutations, right? So this means that if I list them for increasing n, for n is 1, I have 1 state, for n is 2, I have 2 states, for n is 3, 6 states, etc. In the case of random permutations, the number of invariant states is given by the Bell number of 2n's, of 2n. And so what this means is that if I list it for n is 1, I will get 2. For n is 2, I will get 15, 203. It's a very, very rapidly growing number, much faster than the factorial. Okay. So now let me now try to construct what I get when I do now the average over random permutations. Once again, let me start from random unitaries just to have a starting point. So if I have random unitaries, now let me go back to consider the case where I have these unitary matrices acting non-trivially on 2 sides. So whenever I consider that and I average over all the possible unitaries according to the R measure, then what I get is that the object, the resulting object, is going to be a projector. That's very easy to show with the invariance of the R measure. And in fact, it projects on the invariant states that we saw before. The only difference is that since now we are acting on 2 legs, I will have one. I have the same invariant state on both legs. Okay, and then I can basically express this projector in terms of these states in the following way. It's a little bit more complicated than one would like because these states are not orthogonal. So I have to basically, to construct a projector, I have to take the inverse of the Gram matrix. This object here is a very nice object that is called a Feingarten function or matrix. Okay, but I can do exactly the same in the case of random permutation circuits. Now I sum over all possible permutations, my stack as before. I can show in the same way that the thing is going to be a projector and that it projects on these invariant partition states. And I can construct a projector in the same way. Once again, these states are not going to be orthogonal, and therefore I will need to write the projector in this slightly more complicated manner. Okay, is anything clear so far? Now we are going to describe some of the results.
Well, in the case of unitary circuits, you know from each ensemble you draw these matrices, right?
Yes, correct.
What about the permutation?
That's a very good question. So, very good question. So, in the case of unitaries, I draw them from the R measure. the analog of the Haar measure in my case, in the case of permutation, since it's a discrete set, is just the flat sum. So I'm just summing over all of them with equal weight. These will have the same invariance properties as the Haar measure.
So this is the justification, right?
Yeah.
Because maybe some permutations are more important than others.
Yeah. But this has essentially behaves like the Haar measure. So, for example, the average is the projector, which is a good check. Does that make sense? Should I continue?
Yeah, go ahead. I don't see any other question.
Okay, thanks. Okay, very good. So then, once again, let me just stress again, this will be interesting in a second. Notice that for n is 1, for one replica, in the case of unitaries, this projector is trivial, projects on a single state, okay? If I only have one replica, so I have one red and one blue gate, then the average over random unitary is just giving me triviality. I just get a single state, which will basically be the infinite temperature state, as we'll see. Okay, so instead, in the case of random permutations, that's not the case. In fact, when I take n is 1 and I average, I get two states, two invariant states. So the projector is non-trivial. And in fact, interestingly, I get exactly two invariant states, which is the same as what I get for random unitaries if I consider two replicas. Okay, and this will become this parallel will become stronger in a second. So let me start by looking at a very simple object to start with. So let me consider a dynamical correlation function, okay? So which I represent like that. So I take some operator, O nu, at position 0 and time 0, and I consider the correlation function over the infinite temperature state with another operator, O mu, at position at position x at time t, right? So that's a simple dynamical correlation function on the infinite temperature state. And so I can represent this object in the following way in the end of the day, where I now I introduced a slightly simplified diagrammatic notation. So I want to represent my projector Q2n as this box that now is green and contains a number, just to remind myself of how many replicas I'm taking. And in the case of dynamical correlations, I should take exactly two replicas. So I will get here exactly a 2 in the middle of my gate. And that is the case where I have two, as I said before, invariant states. And these two invariant states, if we look at what they are just going to be this state that I represent as a circle, which is a kind of pairing together the two replicas. They are imposing that the two replicas are exactly on the same state. And then I have this other state, which is essentially a flat sum over all possible states of the two replicas as if they are completely independent, right? It's an independent sum. And they are invariant states in the sense that if I act with two of these circles, if I act on two of these circles with my square, then this is left invariant. And that's the same also for the other state. Now, instead, if I act on a state that is a circle on one of the two legs and one of these lines, or a flat state, as I call it, on the other leg, then I get a non-trivial linear combination of circle, circle, and flat, flat. This is exactly the same rule that you have for random unitaries for two replicas, okay? So, yeah, so once again, I don't want to confuse this. So here I'm taking, I'm considering, for dynamical correlations, I'm considering the case in which I have one red gate and one blue gate. So I will refer to this as a one replica problem. So in the case of random permutations, you get the same relations for this one replica problem as you get for random unitaries in the two replica problem, okay? And in fact, this property here can be used to show that the kind of Markov operator, the time evolution operator that I constructed this gate, can actually be mapped to free Fermion. So this is telling you that there is some sort of solvability that is emerging. So, okay, so let me consider what happens for dynamical correlations. So I will have this diagram, and I can essentially use these relations here to simplify the diagram, and in fact to write a set of recurrence relations for the diagram that then in the end I can solve. The idea is that I start basically expanding this operator state in terms of my invariant states, and then I can simplify the diagram using these relations. Okay, so the result is okay. So it has some complicated form. You can compute it exactly, but the asymptotic form is actually very simple. So what we get is we get a correlation that is first of all decaying exponentially with some factor in time. Okay, makes sense. We have no conservation laws, and on top of this exponential decay, there is some sort of diffusive broadening that happens. But perhaps even more interestingly, you can show that this correlation function maps exactly to the average of the correlation function squared if you consider dynamics of random unitary circuits. So the result for random permutations maps exactly to the average of the square in the case of random unitaries. Okay, very good. Let me now consider some quantity that is a little bit more interesting. And in particular, let me look at the entanglement. So what I want to do is I want to prepare my system in a product state, as I said before, and I want to look at the evolution of the entanglement. To simplify the problem to the maximum, I will actually look at the evolution of a proxy. I will look at the evolution of the purity because it's easier to compute. And I will average the purity once again over my random permutation circuits. So if I represent it diagrammatically, then the purity will be represented by a triangular diagram like so. Okay, where now these triangles at the bottom represent my initial state. So of course, now if I take my initial state to be a state of the computational basis, or a flat superposition of all possible states of the computational basis, then I will have that no entanglement is generated. So this state is just going to be a product state at all times. In particular, this one is going to be, in fact, invariant. However, if I consider a random product state at the beginning, then I get an exponential decay of the purity, which I can compute. And I can compare it with the result that one finds for random unitary circuits. And you see that it differs by D-independent factor. It's 4 over D versus 2 over D that you find in random unitary circuits. Okay, so then essentially the question is, can we actually distinguish this sort of dynamics, the dynamics generated by this by the systems that have somehow some classicality in them, some special property of the dynamics, from the instead evolution generated by a completely general quantum systems? So clearly we cannot do it if we just look at entanglement, because we would need to know what is the special basis in order to see that in fact in that special basis there is no entanglement evolution. But if I take a random state, if I don't know the special basis, if I just pick a random product state, I will indeed see an exponential decay of the purity and a linear growth, if you like, of entanglement. So the question is there a quantity that I can compute and immediately tells me whether I have a system that has some sort of hidden classicality like these ones, or instead I have a genuine quantum system? That's the question I want to consider. In fact, I can ask this question to the audience. Do you what would you compute to distinguish the two? Okay, so let me try to let me give you the answer that we found. Okay, in fact, we can pose the question a little bit more generally. So let's say that we have a circuit that is a particular realization of a random unitary circuit. Okay, and then we have a circuit that is a particular realization of the random permutation circuit, where I add on top and bottom some random one-side rotations that are kind of hiding what is the special basis. Is there a simple way that I can distinguish the two, the dynamics generated by the two? And the answer turns out to be that I should consider out of dynamo order correlators. That's something that will, in fact, tell the difference. And it will do so as follows. So if we consider out of time order correlators in random unitary circuits, these have been studied very thoroughly, and they take the following shape. If I plot this correlator as a function of x over t for large times and distances, it will look as a step function essentially. So it will be 0 out of some region that is defined by what is typically called butterfly velocity, VB. And inside this region will be 1, okay? And there is some sort of diffusive transition. So there is a diffusive broadening of the front. So, which I'm not seeing here because I'm plotting things as a function of x over t, right? So in this limit, it really becomes a sharp step function. Okay, so what happens if I compute that for random permutations? Okay, so for random permutations is actually very hard to compute this quantity. So a nice simplification is obtained when we consider the OTOC, but we take one of the two operators in the OTOC to be diagonal. If we take this operator to be diagonal, then we can actually compute it and we can map it exactly to the result for OTOCs in random unitaries according to this mapping. So the OTOC for random permutation is mapped into the one of random unitaries by replacing the local dimension with the local dimension square. It's the same mapping that I had before for correlation functions, apart from an overall constant that I have in front. If I take my operator, so one of them, I took them to be diagonal. If I take the other operator to be random, I see that this overall constant simplifies. And in fact, I have something like 1 minus 1 over d times the result of random unitaries. So basically, what I will see in this case is a shape that looks exactly like the one that you have for random unitaries. But the top part here, the value that for random unitaries is 1, will be 1 minus 1 over d. Okay, but that's actually quite simple to understand why this is the case physically, right? Because essentially, one property of these random permutations is that whatever is the special basis, they have a special basis, and therefore, in that special basis, they will keep separate diagonal and off-diagonal components of operators. Meaning that if I take my O nu to be random, then its diagonal component will evolve separately from the rest, and it will not contribute to the OTOC because also the other operator is diagonal and diagonal operators commute, so I will have 0 contribution from the commutator. And therefore, the only contribution I get from the commutator is coming from the off-diagonal part of the operator. And therefore, if I take a random operator and I do some trivial counting, I indeed get that I should get a factor that is indeed 1 minus 1 over d, just because I have to remove all the diagonal components. If, of course, here I'm assuming that the operators are normalized. Okay, so then that's what distinguishes the dynamics of random permutations. That only the off-diagonal component plays a role. So now, if you take both operators to be random, then the idea is that you should essentially get only the two off-diagonal parts contributed to the OTOC, and this will give indeed 1 minus 1 over d squared. And this can be verified in the large V calculation, but cannot be computed exactly. But so yes, so the quick answer to the question I posed before is indeed that one way to distinguish the dynamics generated by these random permutations from genuine unitary dynamics, and if we want to work in the thermodynamic limit, then what we can do is we can compute OTOC and look at the value of the plateau of the OTOC, which will be lower for random permutations, signaling some sort of conservation in this case of diagonal and off-diagonal part. Okay, in fact, what is going on? Okay, if one is interested in finite systems, then there are other things that will distinguish the dynamics random unitaries and random permutations. For example, in these recent papers here, we showed that random permutations generate different page curves. But with that, I think I would like to conclude with a quick summary. So I introduced the setting of random permutations that are giving a convenient framework to study essentially what is quantum about quantum one-body dynamics, to see where really the full quantumness plays any role. And we saw, for example, that in the growth of entanglement, there is not a lot of real quantumness appearing. Many features of these things, of these systems look quantum. They are in fact even quantum chaotic. We can discuss that later, perhaps. In the sense that their local operator entanglement grows generically linearly in time. And another point that I want to stress is that they can be treated exactly. They can be treated exactly despite the kind of average that we are doing here is much more restricted than the one over random unitaries, and therefore things are generically, whenever the average is getting more restricted, we average over less things are getting more complicated. Despite that, we can still compute things exactly. So with that, I would like to thank you for your attention.
Okay. Thank you very much. So we have time for a couple of questions, Benjamin.
Yeah, thank you, Bruno, for this nice talk. Do you have a physical intuition for the relation between like correlation in random permutation and random unitary, also and the relation with the OTOC? I mean, why there are such simple relations between the two?
That's a very good question. So first of all, let me stress that this relation seems to be there only if I compare one replica quantities for permutations and two replica quantities for unitaries. It is not true when I consider higher replica numbers for permutations. Mm-hmm. And so this should be, the explanation should be something that should somehow involve the fact that only with one replica I get this exact mapping. Mm-hmm. Then, given that, essentially, I think that the idea is that in random permutations, if you look at the evolution of off-diagonal operators, this essentially behaves like the one of general operators in random unitaries. And therefore, yeah, I think that's essentially the only thing I can say. But yeah, I cannot, yeah.
Okay, I have to think about it.
Yeah, no, I also, I thought I had a more poignant answer to that. Yeah, I'll come back to that maybe. I need to think about it as well. Sorry.
I think so.
Okay, yeah. So I'm afraid actually we don't have really time for another question because we have the colloquium at 4:15 by Jorge Kuchan. So I think we have to thank you again.
Okay, thank you very much again.
And so, yeah, so we'll meet here.
Colloquium.
Okay, thank you.
4:20.